All right, so here we go. Welcome, welcome. So as everyone is getting signed on here and joining us, I am gonna have you all use the chat box to introduce yourself and just let us know, in addition to your name, what school you're from, what grade you teach, and what you're excited about from today's workshop. And so we'll just kind of get to know everyone here while folks are signing on. We are a couple minutes ahead of the hour, so we will give folks a few minutes. I appreciate you all joining us on this super nice sunny day. All right, let's see. All right.
So Ashley, I'm good to go. Do you want me to share my screen, or we're going with this, or what's best?
If you'd like to, that'd be great, because I have just lost the chat box.
Okay, give me just a second.
And I will, Caroline, I'm gonna make you the host for right now.
Okay. Ooh. Huh, Ashley, it's asking me to open my system preferences to share a screen. I've never had to do this before. Since we're not in the webinar, I wonder if it's changing something different about my computer. Hold on.
Oh, interesting. Yeah, I can go back to sharing if needed. I had to retrieve the chat box from behind my.
Yeah, I'm getting an odd message. It says Zoom will not be able to record the contents of your screen until it is quit. So I might have to dip out. I'll try dipping out and coming back in, just letting you know.
I'll just share for now. All right, well, welcome everyone. So excited to see folks in here from all over, different schools, amazing. Cool. We have just about one more minute while folks are getting signed on. I love that I'm seeing some of you in awesome locations. Looks like we've got some green screen action. We've got some back porch action. This is nice. I love this. I was just saying earlier, I was like, thank you all so much for being here on this beautiful, beautiful day. I know that probably the last thing anyone needs is more screen time right now. So I'm very appreciative of you donating your time to spend a little bit of it with us, learning about some cool stuff. I'm pretty psyched about today's presentation. We've been working on this program for a little while, and we actually used COVID as a kind of excuse to kick it up to the front of our radar. So we're pretty jazzed about it. Just to, let's see, so it's 4 o'clock now. I'm going to start just going over the agenda kind of quickly, just to give you a sense of what we're going to be doing today, and hopefully the last few folks that are getting adjusted and getting signed on will join us. So today's session kind of has 2 different parts. We are, oh, whoops, I realized that I'm not sharing in presentation mode. Sorry, I have 2 screens here, so I'm looking at 2 different things. So for today's session, we're going to start actually by hearing a little bit from the Lake Champlain Basin Technical Coordinator, Matthew Vaughn, and he's going to share a little bit about the long-term monitoring project, which is actually the project that the data for the CODAP program that I've designed is from. And so we're going to hear a little bit about sampling, a little bit about some units, because that's still something that our college freshmen struggle with. So I'm sure for all you high school and middle school teachers, when you start getting into units, things get a little tricky. And so we're going to hear from Matt, and then Matt's also going to talk about how that data is actually used, so what they do with that data to then make management decisions. I will talk about this CODAP program that you have maybe heard of, maybe not. It's Common Online Data Analysis Platform, and so I'm going to talk about how I feel this program is really accessible for students to use when you start getting into kind of basic data science. And then we're actually going to spend some time exploring some of the challenge cards that I've put together on this data set. So just so you can do what you need to get prepared, we will be actually kind of like not leaving Zoom, but opening another window and doing a little bit of work in this in a web browser on CODAP, just to kind of show you and get familiar with that. And then we'll have probably about 10 to 15 minutes at the end of our session, and we will do questions. So if you have questions about kind of what we've gone over, how you might use this, you can ask. I think it's a good time to ask Matt any technical questions you might have. We will do that. So, all right, without further ado, I'm actually going to turn it over to Caroline, and Caroline is just going to talk through some of the tools we're going to use in Zoom today.
Cool. Ashley, are you the Vanna White in this one then?
Yeah, I'll Vanna for you. This is a new change of scenery.
All right, so lots of familiar faces. So hi, everybody. I'm Caroline Blake. I work with Ashley and Nate, but there's lots of familiar teacher faces, although there's only 6 of you showing up on my screen right now, but so it goes. I see Jackie and Molly and Andy, so I at least know 3 out of the 4. Sorry, Patty, I don't know you, but excited to talk to you all. So for this raised hand setting, I'm sure you've all used it by this point, but just throughout the presentation, if you have any questions, just press that button. If you haven't used it before, if you click the participants button down at the bottom, you should be able to then have that pop up off to the side, and there's a raised hand button. Or just do a shout out in the chat if you're having trouble finding that as well. And then our polling options, just to make it a little bit more interactive and hearing what your all's thoughts are on things. Ashley, Nate, Matt, or I will launch a poll with asking you all a question. You could answer it right then and there on your screen, but if for some reason it's not popping up, just throw the answer in the chat box, and that's our makeshift option. And then last but not least, if you're looking for like assistance for something not going right or having a question about just how CODAP is working, throw that into the chat box. Nate, Ashley, and I are going to be kind of moderating that chat box and then reaching out to you all individually to try and help you brainstorm that technical question. All right, Ashley. All right, and then without further ado, let me introduce Matt, and I'm going to clear out some screens. So Matt oversees scientific projects funded by the Lake Champlain Basin Program and works closely with the LCBP Technical Advisory Committee. He holds a PhD in natural resources from the University of Vermont, and a Master's of Science in Hydrological Science from UC Davis, and a BA in Physics from Middlebury College. His research focuses on the influence of land use and land cover on water quality in the Lake Champlain Basin. Matthew has a love for the outdoors, woodworking, and music. He lives with his family in the old north end of Burlington. We might even get some guest appearances. We've seen the 2 little boys so far, so maybe they'll pop in and out. And then today he'll be sharing his expertise in data analysis. Matt will provide an overview of the Lake Champlain long-term monitoring program and how the data for that program is used to calculate concentration and load for a variety of water quality parameters. So without further ado, Matt's going to start sharing his screen, and I'm going to fade to the background.
All right, thank you very much for that wonderful introduction. Nice to be with you all. I'm just trying to navigate how I can, okay. Can you all see my presentation here?
We can, yeah. I think you're not in presentation mode, but that.
Okay, how about now? Are you seeing the right one?
We are seeing it, but we're seeing the presenter view. So we're seeing your.
Let's try this. How about that?
Better, amazing, perfect.
Did it work? Okay, cool, thank you. Yeah, so great to be here. I'm excited to share some of this work and to help you all use this data. It's really exciting that it's out there on the internet and available for anyone to use and to learn from it. So just a few things about the Lake Champlain Basin Program. Our mission is to coordinate and fund efforts that benefit the Lake Champlain Basin's water quality, fisheries, wetlands, wildlife, recreation, and cultural resources. So it's a really broad, far-reaching mission. We have a lot of work going on, so I'm not even going to try to touch on everything we have going, but you know, the basin is a big place. It's split between 3 jurisdictions, Vermont, New York, and Quebec, and we work with all these great partners to move these things forward. So I just want to talk about what we call our adaptive management strategy or approach to our work. We call it the pressure state response model. So here, can you all see my mouse if I do this? Okay, I'm getting a nod, good. So the pressure is something like pollution. We're going to talk a lot about phosphorus and chloride today with the data we have available. So that's something that's exerting a pressure on our ecosystem. And then we're able to measure the state of the water quality of the lake or the tributaries that drain into the lake. And then we're able to come up with a response or what we can do to improve the state or the ecosystem of the lake. So what we're talking about today is our actual measurements that we've gone out and taken by collecting, bottles of water and bringing them to a laboratory. So we're really focusing on the state. What is the state of our ecosystem so that we can formulate this response here in blue. And just one more piece on the state. We issue a State of the Lake and Ecosystems Indicator report every 3 years. So the last one was in 2018. This is available online on our website, and it's written at a 7th grade reading level. It's available to all of you. Hopefully all or many of you have seen this, if not all of you. And we try to make it accessible and have graphs and text that people can really approach and get a lot out of it. So on to the long-term monitoring program. This is really going to be the focus of today's lesson. These are the sites that were identified in the early 1990s as really indicative of if we're able to monitor the health of these sites, we can really know what's going on with the lake ecosystem. So you see these lines in black here. These are the tributaries, the rivers that drain into the lake. And then the blue here is obviously the lake itself. And so these boxes are tributary sampling locations, and the dots here are spots on the lake where we actually go out on boats. We have teams in Vermont and New York going out and measuring water quality, measuring biological indicators all the time, just about every day in the spring, summer, and fall. For today's lesson, we're going to be really focusing on the tributaries. So these are, again, the rivers that drain the landscape. Here is a photo of one of our tributaries during Tropical Storm Irene. So I love this photo. I mean, it was a big deal for those of you who were around for this storm, but it really demonstrates the link between the land and the water. You can see this plume of sediment coming down and emptying into the lake. And this is why we really need to monitor our tributaries to see what's being delivered to the lake each year. And I'm going to be talking about how we actually do that. How can we determine how much phosphorus, nitrogen, these are important nutrients, chloride, this is an element that's used for road salt, but actually has impacts on our lake ecosystem, and sediment itself, just the actual suspended sediment in the river makes its way to the lake. So these are things we can actually measure and estimate the loads into the lake each year. So there's two terms, this may be familiar to most of you, but just to make sure we're all on the same page, we're going to be talking about concentration here at the top and load. Okay, so concentration, in this case, this graphic is focusing on phosphorus, but it could be about anything. It's the mass per volume in amount of water. So in this case, for phosphorus, we often talk about micrograms per liter, but it could be milligrams per liter, it could be grams per liter, it could be kilograms per cubic meter. It's just anything that's measured in mass per volume. That's a concentration. How concentrated is it in the water? And then load is a little bit different. This is the amount of mass per year or mass per time. So in this case, we often talk about MT, which is metric tons, and that's 1,000 kilograms of mass. And we just use kind of a big unit because there's a lot of stuff coming down the river. So that's a convenient one for us to use. And we talk about years because that's a convenient time period to check in on with our data. So for the loads, we're talking about metric tons per year. Okay, and actually this is a visual we like to use. This is an African black rhino. It weighs about a metric ton. So when we're thinking about what a metric ton looks like, you can think about this rhino floating down the river. All right, so the way we calculate load is by, just briefly, it's by multiplying the concentration of something by the discharge or the amount of water going downstream. So this plot has two lines on it. the blue is the discharge, or the amount of water, and that's volume of water per time, and we measure that in cubic meters per second. So volume per time, cubic meters. Think of a big box with a meter on each side, and per second, we all know what a second is. So it's a lot of water coming down. And then the green line here is the phosphorus load, metric tons per year. And this is for the Winooski River, which is our largest tributary. And one thing that you'll notice is that these two lines really follow each other. And that's because the more water is going downstream, the more phosphorus is going to be carried along with it. So again, thinking about that tropical storm Irene, 2011 is really kind of off the charts here for both water, and because there was more water going down, it also carried more phosphorus. So these two things are really linked together. And if you think about it mathematically, it makes sense because the load is found by multiplying the concentration and the discharge together. So this line is calculated by using this line. So that's why they're correlated. And if anyone wants to, I guess, Ashley or Caroline, if you see questions coming in, feel free to interrupt me and I can clarify as I go. All right, so Ashley asked me to talk a bit about units. And she said, I guess their freshmen have trouble with this. So it's definitely something that I use just about every day in my work, is thinking about units and how we can use them, how we understand them, and how we can communicate better with our units. So I just wanted to run through an exercise you might find useful with your students. And maybe you already do this, but this is how I think of units usually. So again, concentration, we're going to be talking about milligrams per liter. So it's a thousandth of a gram per liter of water, like a Nalgene bottle is a liter of water. And then discharge, again, that's the amount of water going into the lake at any given time. So that's cubic meters per second. And these are just kind of conventions. This is what we often use, cubic meters per second. Now, if we multiply those together, we're able to come up with a load, and that's the mass per time, or metric tons per year. So the way I think of doing this, and this is the tool that I use very frequently, is when you take something and multiply it by 1, you always get the same thing. And you can get 1 by having the numerator equal the denominator, of course. So in this case, and I broke this up into more steps than you need to try to demonstrate how you could do this, or how you could work this out with your students. But for example, we want milligrams per liter times cubic meters per second, and we want to end up with metric tons per year. So for multiplying by several different versions of 1, we can look at 1 gram is equal to 1,000 milligrams, and then we can cross out the milligrams here and here. And then we can look at 1,000 grams is equal to a kilogram, so that's another time multiplying by 1. And so on. And here we have 1,000 kilograms is equal to 1 metric ton. So we're canceling all of these things out. Besides, what we're left here is the metric tons for mass. And then for volume, we can just convert the liters, the cubic meters into liters, because there's 1,000 liters in a cubic meter. And then for time, I just go through these 3 steps here. There are 3,600 seconds in an hour, 60 seconds per minute times 60 minutes per hour, that's 3,600. There are 24 hours in a day, of course, and 365.25 days in a year because of those pesky leap years. So you can see the red units is all we're left with when all of these things cancel out, and we can convert from this product here by just multiplying by our number 31.56, and we end up with metric tons per year, how many black rhinos in the river per year going into the lake. And for phosphorus, for example, we estimate that we, as a basin, deliver about 921 metric tons per year of phosphorus into the lake each year. And that's something we're trying to work toward reducing as part of the EPA regulations and the work of New York, Vermont, and Quebec. Okay, so I'm just going to talk about how the basin program uses this data to come up with our estimates for load for each year. So we have 18 tributaries. We actually have 22 that we monitor, and 18 of them have records long enough to really look at trends over time. So we look at 18 of these rivers here. And again, we're using these long-term monitoring program samples. These are, again, people going out to the tributary during a storm and during low flow during the summertime and grabbing bottles of water that we're analyzing for concentration. And then we need to develop a model to predict concentration for when we weren't there to sample it. And this is the really tricky part. Introduces a lot of uncertainty because we know what the concentration was when we were there, but we don't know what it was the next day because we didn't drive there because it was Saturday, or maybe it was a holiday, or maybe we were somewhere else. So we need to develop a mathematical model to predict that concentration. And then we can multiply that by the discharge, or the amount of water going downstream. And that we do know really well because the US Geological Survey measures it every 15 minutes. So we know that a lot better. We have a good idea of how much water is going downstream. So we have that model of concentration that we're developing. We're multiplying it by the amount of water, and then we get the load, and we can add those all up for an annual total. And then we also, like I showed you with that graph, with those two lines that were kind of following each other, when we have a storm like Tropical Storm Irene, it really throws off the water quality trends because we might have a dry year one year and a wet year the next year, and we don't know how we're doing with our water quality goals. Was that, were those changes due to something we did, or just because it happened to be a dry or wet year? So we also do some fancy statistics to try to reduce the influence of that annual flow variability so we can see how we're actually doing toward our water quality goals. And then we also use math and statistics to determine if there's a trend over time. Are things getting worse? Are things getting better? Or are they staying the same? And we can do that for the entire period of record, or we can break it up into early period and late period. Was there a change over time? And that's something that you're going to be going through with a CODAP data set later in the lesson. And so here's an example of the plot. This is the chloride load. Again, this is chloride comes mainly from road salt. And winter applications. So we see that over time in the Winooski River, again, our largest tributary, the load of chloride into the lake through the Winooski has significantly increased. This black line is what we've actually measured and estimated. And then this gray line is that kind of trend line without the influence of that annual flow variability. So just wanted to mention, I'm wrapping up here, just wanted to mention that with all those sources of uncertainty, we can't be there every day. We're just taking a snapshot of water quality and concentrations when we're able to go, and we're modeling it. There are more advanced tools out there that they're starting to use. So this is a buoy, for example, and this buoy actually uses light that shines through the water and measures water quality on a minute-by-minute time scale. So we can reduce that uncertainty of not being able to be out on a boat every single day or every single hour by just putting a buoy out there and letting it measure water quality. We can do a similar thing in the tributaries by putting sensors in the river, maybe mounted to a bridge or to some other piece of infrastructure to measure water quality on a minute-by-minute basis. So this is something that the Basin Program is going to be working on next year. The Lake Champlain Sea Grant already has buoys out there today collecting this great data. So I think that's all I had, unless you wanted me to cover anything else, Ashley.
No, I think that's great. I'll have you chime in when we get to some of the higher level challenge cards and some of the statistical significance. Thanks for that overview.
All right, you're welcome.
All right, so now I am super excited to share with you. I'm going to start talking about a program that I've been using called CODAP. Matt, can you add me as the host again so I can share? So I'm going to walk you through this program. I ran into this program while I was taking a course, a climate change collaborative meeting, and we met with folks from the Gulf of Maine Research Institute, and they were using this program, CODAP, to look at
So did Ashley cut out on other people's screens too? Okay, yes. So I can't pretend to be her, nor do I know her presentation, but I know the goal was for me to take over the screen so that when she pops back on in 30 seconds, that she can then teach from my screen. So bear with us as we, I wonder if I can even do that because she's in the, She's the host, and the only way that I can share my screen is if I'm the host. So we'll let her jump back on. and see what happens. Unless, Nate, do you have any other suggestions? Oh, now I should be good. All right.
Yep, so it looks like Matt's the host now. So Matt, if maybe you want to toss that over to Caroline so she can get the PowerPoint thrown up. Yeah, there you go.
Cool.
Yeah, should be good.
All right, people should be able to present. All right, so this is where it actually left off. So does anybody have any questions starting off as we're kind of waiting for Ashley to jump back on?
I am here, Caroline.
Oh, nice. Well, still, does anybody have any questions, I guess? Feel free to pop them in the chat box. But Ashley, yeah, I'll be your Vanna White, so tell me when to go to the next slide.
Thank you so much. Sorry about that, everyone. Okay, so where were we? All right. Okay, you can go to the next slide, Caroline, and I'll start jumping in talking about CODAP. So CODAP stands for Common Online Data Analysis Platform. So it's free. It's just a web browser. It's not an app or anything like that. I discovered this while I was working with some folks from the Gulf of Maine Research Institute. So they have been using this to help students understand climate change by using long-term data sets on winter minimum temperatures for the Gulf of Maine, which, as some of you may know, is one of the fastest changing regions right now for climate change in terms of some of their long-term temperature data sets. And so they actually walked us through how they were using it as if we were students, and it was a really powerful experience. And I was just really amazed by, as you can see on the screen here, some of the visualizations that you're able to create that I had previously only really had experience in kind of my master's program using R in pretty high level statistical software. But I know that visuals are so powerful for students. And so I kind of took some of their work, and we worked on some options for the Lake Champlain Basin and what we could do. And so I started pulling basically long-term data sets and just playing with them. And I realized that it made a lot of sense because I wanted the project to be ongoing, to use something like the LTM as the base for the data set in a way that we could continually add each year more information. But also, for those of you that have worked with us and our staff during the stream monitoring, we're trying to find ways for students to, collect more accurate data, so using different sensors, but also finding ways students can plug that data into bigger data sets to see how their information fits with other trends in data. And so basically, I was pretty psyched about this, and this is going to sound a little bit like I am a rep for CODAP, but I can assure you that this is unsolicited. But I love it because it's free, it's web-based, and CODAP says it's really for grades 6 to 14, but I feel like it's pretty versatile. It just depends on how you set up the data set you're going to work with students in. And so I'm going to share actually a Google folder at the end of this webinar that has a ton of information. It'll have all the links, everything you need, so don't stress about any of that. I'm going to go over a bunch of stuff on the next few slides. And it's a lot, but just know that I'm going to give it all to you later, so don't feel too stressed. And so if we go to the next slide, I'll kind of tell you what I've developed with just amazing support from Matt Vaughn from the Basin program on this. So I'm going to share with you today 2 different data sets. And so one data set is the long-term monitoring tributary data set. This is just from the Vermont TEC website. You can actually just download all that data in an Excel form. I reformatted it so that it would fit into CODAP and work the way that I wanted to, and kind of deleted some of the parameters that were a little extraneous. And then the second data set that I'm going to show you actually is, so from some of those graphs that Matt showed you from the model that he ran, we're actually going to use some of the concentration and load or flux data that Matt had for a technical report that the Basin program put out in the last year on concentration and load. So that's super exciting as well. And the idea is that this program is really scaffolded so you kind of get students just playing with the program. It's very, if you use a Mac, I think it's very much like a Mac program in the sense that it's pretty intuitive, it's click and drag. I feel like unlike even Excel, where you really have to just know how to do things and understand formulas and things like that, this kind of eliminates some of that, so some of those barriers. So the challenge cards that I developed for this are based in the sense that you can kind of run students through 3 rounds. And so we're going to do a couple cards from each of these rounds today together, kind of synchronously. but you could really facilitate this in a variety of ways. So round one starts with getting students just familiar with the program. And so just kind of learning how to do things, how to move things around, and then also just being comfortable with having a lot of stuff on the screen, having a lot of data there, and knowing how to move that and shift that and not kind of be overwhelmed or anything like that. Round two starts to get into, okay, how do you now manipulate this data? If I want to make something, if I want to show something, how do I do that? And so looking at some of the graphing skills you can do, and then just kind of exploring all of the data that is in that set. Round three actually starts using that LTM concentration and load data set. And so for this data set, you actually start to think about making decisions based on the graphs that you're looking at, and you start thinking about making kind of inferences or trying to understand what's happening on the landscape based on the data that you're seeing. And so something that's really unique about that I'll share with you, there's little components that are actually pulled from the Lake Champlain Basin Technical Report, and Matt will talk a little bit, elaborate on those, but it kind of tells students, no, this is what the organization using this data actually found. So they get to walk through it, come up with kind of their own conclusions, and then see how it compares. So that's kind of a unique option. So I am going to do something right now, and I have high hopes that it's going to work, but I'm actually going to share my screen in a second here. Caroline just needs to give me permission, and I'm going to walk you through showing you the first data set just to get you oriented before I set you loose in here. And so let's see. Okay, so you all should be seeing a web browser right now with some data in it. Okay, awesome. And I'm still seeing your faces, so that means I haven't lost you yet. All right, so this is the data that I uploaded here into CODAP. So this is the CODAP interface. You'll see that in terms of kind of buttons and options, it's pretty limited. There's not a ton. What I'm kind of gonna show you is just the way that this set up. So I uploaded this via a CSV file in here, and I had kind of gotten everything ready before putting it in here because it actually is a little tricky to manipulate things once, to change the data once it's in here. It can be done, but gets a little wonky. So now you'll see that I've got things kind of broken up. I have state is kind of one classification. So you'll see that when I click state, it starts highlighting each of the tributaries and where they're from. So I can kind of scroll through, and I should have province in here for Quebec. And then you can also click on just a tributary and look at that data set. And so what is really cool, just get ready to have your mind blown. So I'm gonna make a graph. I'm gonna click this graphing button. I'm actually gonna pull this to the center, make it a little bigger so that you all can really see what's going on here. And I'm gonna just real quick, I'm gonna create a plot, and I'm gonna do, let's see, just do total P, and we're gonna do it over, for right now, we're gonna do it over a year. And so it's going to take a couple seconds here because there's quite a few data points in here, but you'll see that basically you're watching the data move into how it's set up in this graph. And so we're going to go through, you can see there's some outliers. You can actually click on these. It'll show you what they are, which is kind of neat. And there's a couple other cool features that we're going to walk through together, but I don't want to give everything away. So this is how it's set up. What I love about this, once you're in here, so I have basically shared, I'm going to share a link with you. Once you open that up, it's your frame. So you're not altering the original data set. You're actually, it's like Google Sheets, like you're creating your own. And so you'll be able to save that up here, and it actually just will save to your, it'll save to your Google Drive. So it's kind of neat in that sense, and students can kind of create their own workbook and then simply share the link with you. You can get a shareable link, and then you can log in and look at what they're doing. They can also take pictures in here, which is kind of cool. And there's a lot of cool features. Okay, so I'm going to stop sharing this for 1 second. We'll go back to, I'm going to give Caroline permission to share, make host. Okay, switching back to you, Caroline.
Sounds good. Stand by.
Stand by. Okay, and so what we're going to do is, okay. So let's see, I just want to make sure I covered everything. Awesome. Okay, and I'm going to share a guide that has a bunch of like just general directions on how to do things. And looking at that data set, if that felt like overwhelming or like that wouldn't be great for your students, it's actually incredibly simple to just delete some of those parameters. So if you want to just look at like chloride and phosphorus or total suspended solids, you can kind of clear everything else out and just keep those. So to round one of these challenge cards. So what I'm going to have, I'm going to put a little already might have done, and we're going to all just spend a couple minutes playing with.
Actually, it's hard to hear you. I don't know if other people are having the same problem. It sounds like you're blowing in the wind.
Yep. I actually think, Catherine, that's you. If you could mute yourself, that would be incredibly helpful. Okay. So looking at this first round of challenge cards, Nate's popping the link in the chat box right now. Basically, if you were facilitating this in person, one way that I feel like it's really successful is if you actually have these challenge cards printed out, they're front and back. And I'll give you a link to the challenge cards a little bit later. And then students actually just get the whole set and they just start playing with it and figuring out what they can do, what they can't do. And there's actually a little label that comes, there's 3 labels, kind of like, I'm stuck, I did it, or I haven't tried it yet. And students just flip through the cards and they kind of place things where they're at. That's how we did it at GMRI. It worked super well for our group. And then, but virtually we're going to kind of do it together. So I'm going to give you a challenge card and you're going to try and do it. So if you want to go ahead and open up that link and start playing with it, our first challenge here is going to be to plot a distribution. So I just gave you a little bit of a hint on how to do that, but I want you to try and do that first. And then we're going to kind of build on that. So basically take a minute, check out that interface, try plotting the distribution. When you're finished with that, like once you've got it, if you could actually just give us like a hand raise in the chat box so that we know that you are all set. And so feel free, since for some of you this might be your first time looking at this, just kind of clicking around, seeing what is in there, testing out a couple of those buttons. And then what's super nice is if you are in there and you are having a hard time, Caroline, you can go ahead and click this slide. So the back of every challenge card has a hint. It has some of the graphics, some of the instructions. So if you're really, if a student's struggling or if you just need a little hint, you can kind of look on the back and see, okay, I need to do this. This is kind of the order of operations here to accomplish that.
And I think Ashley did a great job with this. I pretended that I was one of you all yesterday and went through all of these because I truly had never opened up the program before. So those hints really do guide you to where you need to go. But again, we're here for the extra support if for some reason your computer is deciding it doesn't want to do one of those functions, etc.
Yeah, and if you need help, just toss a little note in the chat box. If folks are willing and they want to turn on their screen, I actually will use a little thumbs up gauge to see where folks are at with this challenge card. So if your screen is on, could you give me like a thumbs up? And if you need another minute, maybe like a 1 or a 2 on this interface right now. Okay, 1 minute. Okay, we'll do 1 more minute here. And so something else to think about while you're, I know a lot of you have actually been collecting a lot of data with your students. And so even uploading student data sets in here could be a really cool way as maybe even like an intro prior to diving into some of the LTM data as a kind of a scaffolded experience to get students a little bit more familiar with kind of using this interface and playing around with data. Awesome. Oops. I've got a cat participant over here that is enthusiastic about data. So we're going to go to the next challenge card, which just basically builds on what we just did. So if you're not quite there, that's okay, because you're going to have another second to work on it. So for this challenge card, this is asking you to graph two attributes. So putting something on both the X and the Y axis, and starting to organize the data that way. And so Caroline has just given you a little hint on how to do that if you're not quite there. One thing that we did with our set of challenge cards is we actually tried to make things pretty specific. So the Gulf of Maine Research Institute has a more generic set that's kind of just like getting to know CODAP. But when we went through it with our staff, we felt like it was actually really helpful to kind of guide students and help them make meaning a little earlier rather than just putting things on various axes. So we've kind of, said, okay, display total phosphorus over time. So giving them how to set that up. And then giving some hints on how to make that happen. So, as I mentioned earlier, round one is really geared at just playing with the data, learning how to do things in CODAP, and getting kind of familiar with larger data sets that are maybe a little bit more confusing. So I'll give you, do people need another minute on this as well? I feel like some of you went ahead and did this probably on the first slide. Okay, so we are going to go on to the next slide, and we're going to look at, this is a really cool feature, I think, if you're doing something with data in place, mapping an attribute. So if you select the LTM tributary monitoring sites table, you can actually create a map of where those sites are. So it'll show you kind of almost in a Google image way where this map is, and you can interact with it. You can move things around. You can kind of click on the points. It'll tell you which tributary that is and where it is. And so that's kind of a neat feature, especially just, I think, getting students familiar with the watershed and where things are, and maybe zooming out a little bit and figuring out where they are, but where some of these other kind of areas are is super helpful. Okay, so I'm gonna actually Caroline's gonna launch a poll for you that's gonna ask you a question about this graph. Let's see where you all are at.
Let me try to figure out, I'm not seeing the polling option like I usually would, Ashley, at the bottom. Let me, oh, gotcha.
Yeah, Kara, I'm gonna answer your question.
I'm good.
Well, Caroline's figuring that out. So you can, there is a little like kind of minimize button.
Yeah, no, I got it. The only thing is, Ashley, when I launch it, I think it's gonna launch all of them.
Oh, they're all set up as one. Okay.
I think there's I set them up. The first two questions are together, so I wasn't sure if you want them together or separate. But the feedback is separate from the first two.
Okay, great. Yeah, you can launch them the first two right now, Caroline. That's fine. Okay, so which of the LTM sites is the farthest north? The Ausable, the Winooski, the Pike, or the Salmon? And Kara, just to finish answering your question about that, there is a little spot to kind of minimize. I'm not sure if you found that. It's in that top bar. It allows you to kind of click on that, and there should be a little, okay, you're good, great. So yeah, go ahead and vote on that. And then the second question that's there, we haven't really talked about this, but I bet you all can answer it. What watershed factors might contribute to high nitrogen concentrations? So heavy applications of fertilizers, agriculture, on agricultural lands and lawns, acid rain, stormwater runoff, or all of the above. And so we will share those results in just a second once folks have voted.
I'm gonna end the poll. I'm gonna share results.
Awesome. Yeah, so Pike River, definitely, that's up in Quebec. And then heavy lawns and fertilizers for sure, but then also all of the above. Acid rain and atmospheric deposition can definitely contribute to nitrogen concentrations, as well as stormwater runoff. Awesome. So we're gonna go on to our next challenge card, and I think we're gonna jazz it up and we'll go to round 2. Okay, so this is where things start to get a little bit more advanced. So if you have a graph on your screen right now, and if you don't, just go ahead and make a quick one with kind of something on the X and Y axis, usually over time, but whatever works for you. And I want to show you how to add a color scale like this. And one thing that I think this works particularly well for this data set is actually to identify and group tributaries. So once you have your graph set up like this, kind of this little picture in the challenge card here, go ahead and take the tributary header, click it, and drag tributary and drop it in the middle of your graph. And this is going to actually create groupings for each of the tributaries that show you those data sets. And then if your graph was really small to begin with, it's going to look wonky. That there is a button on the top right of your graph that actually is like a little window with like expanders. If you click that, it will automatically like readjust your screen so that you're seeing. You can also click and drag from the corner. And all of these little tips that I'm mentioning are actually different challenge cards from round one that, had you done the full set of round one, you would have played around with these skills already. And so that's kind of neat. Now, the other thing I'll show you real quick, on the right side in those kind of graphing tools, there's a little eye image. If you click that, that'll allow you to hide or view data. So try clicking on a tributary like the Au Sable or the Winooski or the Salmon, and then click on that eye and actually click hide unselected data. This will now allow you to see only the data for that tributary, which is a little bit easier to look at, I think, in that graph. And then from there, if you re-click that top right icon with the little box with the little expanders, that will reset your graph. It'll rescale both the X and Y axis to that data set and make it a little bit more easy to view. So can I get a thumbs up if people are all set with that? Cool. Okay, does anyone need any more time? Okay, so going on to the next challenge card, we are going to add a least squares regression line, which can be challenging in Excel, but is actually quite simple here in CODAP. So on the right-hand screen, you're going to see a little, look through those graphing options and see if you can figure out where that least squares regression line is, and it'll fit that to the data set. And maybe Matt, while they're doing this, do you want to chime in and just talk about the statistical significance of a least squares regression line and how it's helpful in data analysis?
Yeah, sure. So you can see from this exercise, it's usually pretty easy to throw some points on a graph, but of course, to make meaning out of it and to make decisions based on this data, we want to be able to summarize it and understand if there's a trend over time, if things are changing, for example. So that line, many of you are probably familiar with it. It's just a way to draw kind of a best fit line through the data to kind of model what the data is telling us. And it's the calculation is really to minimize what we call residuals or errors or the distances from those points to that line. So it kind of optimizes and fits a line. In this case, it's just one line. You can also have more fancy models with squiggly lines or multiple lines fit together. But anyway, that, the equation for the line tells you the slope and then where it intercepts the vertical axis. So I think if I'm reading the one on your slide here, it's kind of hard for me to read actually, but if that coefficient is positive, then generally the correlation is a positive one. So the x-axis will increase along with the y-axis for your points. And if it's negative, then the line would be decreasing. So that slope tells you a lot about what the data is doing. However, that R squared value, it's called the coefficient of determination. The closer that is to 1, the better that line describes your data. So for this one, I'm seeing it's 0.047. So that's telling us that line, you can always draw a line, but it may not actually describe your data very well. So it's a good tool regardless to just see, as a first check to see what the data is telling you. But if the line does not fit your data well, then it's not really going to be describing much of anything. So that's something to keep in mind when you're working with your students. Is that enough or too much?
I think that's just right.
Okay, great.
That's great. Thanks, Matt. All right, so we'll go on to our next round 2 challenge card. Oh, we're just right into round 3. Okay, so this is where things get a little bit more interesting, and there is a little bit more prompting and thought processing in this, and so kind of question asking in terms of getting students to look at the data and think about what might be happening. So for this example, each of these cards actually is a little bit longer, so you'll see that this is kind of broken up, but it's kind of the action at the top, but then it's followed by prompts. And so while students are graphing this, you're asking them to think about, do you notice any trends over time for each tributary? With one tributary, calculate and compare the median phosphorus load for all the years before 2004, and then all the years during or after 2004. And then which years have the highest loads in each tributary, what factors might contribute to this. And so this is where you start getting students to think a little bit more about what's actually happening in that data, explaining, you know, historical events, but also explaining what can't be seen with the data, which I think is really interesting. And so I actually think, Caroline, if you click one more time. So the bonus of these is that in addition to the hint on each of these cards, there also is an excerpt from the Lake Champlain Basin technical report. And so this, after students have kind of brainstormed and thought about it, they can see how their answer or their thoughts line up with actually what was reported by the organization that's using this data. And so for this one on total phosphorus and thinking about kind of load for total phosphorus over time in Little Au Sable and the Winooski, Matt, I don't know if you want to just talk a little bit about what was in the technical report that you wrote about that.
Yeah, sure. So so this one is based on a data set that's a little bit different. It's turn my video here so you can see me. So what you were just working with are the direct measurements from the long-term monitoring program. So what are the, you know, what was measured from the bottle of water that we went out and grabbed. This next round 3 are kind of using the modeling outputs that we came up with that I mentioned earlier. So we're using statistics to try to best estimate the load of phosphorus in mass per time or metric tons per year each year to the lake, and that data set is available to you, you know, in a separate link and to your students. And so so Ashley, did you want me to kind of give away the answer here and tell folks what we found?
I think so, yeah. And then I'm going to have Nate post the link so you can see the next data set. That'd be great.
Yeah, so and this is a good lesson for your students, that it's when you go looking for answers, you don't always find an increasing or decreasing trend. Sometimes, you know, a boring answer is a really interesting one. So for this one, for total phosphorus, what we found in general was that there really were not a lot of long-term trends in total phosphorus loading from 1990 through 2017. And so you can look at that as, you know, a bit discouraging because we've done a lot of work and we're not really seeing all the results just yet. And we do see some decreases in some tributaries and actually some increases in others. But also with a lot of all these pressures on our landscape and on our ecosystem, you could also see it as a positive that it's not getting worse in some areas where you might expect it to, based on our work. So that's a brief overview of total phosphorus. Do you want me to cover anything else, Ashley, or is that good?
I think that's great. So folks actually should be now, you can click on that third data set. And so Matt, I don't know, is there anything else you want to say about the data set that we're sharing for round 3? This is kind of the one that I pulled from your model. If there's any other notes you want to toss in there about that.
If you want to get geeky about it, you could look in the report and see how it was done, but it was a lot of statistics and modeling based on some programming that others had done and I worked with. But really, it's a nice data set for you to work with, I think, because it's kind of binned into years. You know, it has an estimate for each year for concentration and load, and it kind of summarizes what the long-term monitoring program data told us. Whereas the first one you were just working with, it's the reality of what we found, but it's a bit spotty and you know, just whenever we happen to get out there and grab a bottle of water versus here is the total load for 1993 and here it is for 1994. So you can really have that continuity and see what the chloride concentration, for example, did over time in the Winooski River. It should be very clear to your students when you plot that.
Yeah, that's great. And so the other thing that I was just going to say about this data set is that it's definitely a bit simpler in kind of addition to only focusing on load and concentration for each year, which is nice. I think if we go to the next challenge card, we have a question about nitrogen. Yep. So the next question is asking you to plot nitrogen. So this actually was where that polling question from earlier came in, looking at the nitrogen concentrations for each of the tributaries, and then kind of figuring out which tributary is the highest. And so the way that this is set up, which is kind of nice, is you as a teacher have an idea of what the answers to all of these things are, and I'll actually share with you the link to the Lake Champlain Basin Technical Report where you can actually pull graphs and kind of look at the more sophisticated statistic analysis that Matt did. But your students don't know that, right? And so they're getting to these conclusions kind of on their own, which is really unique in a way that I think is less frustrating than some other programs, in my opinion. So this is kind of neat to figure that out. And then I think, Caroline, if you want to go to, great, yep. And then this is what the Basin program reported for that. So after you've gone through and mapped this out and looked at it, you can kind of start to make some findings. And Matt, I don't know if you want to weigh in again here on kind of on this card and the notes from the technical report.
I think it speaks for itself. You know, the nitrogen story was really interesting. The Pike River is kind of our standout tributary. It was a lot higher than the others. And I meant to mention this earlier, but this work, the report that Ashley's been referring to, and when you're all working with your students with this data, I think of this as the what, not the why. This is what we were able to measure. It's the state of the lake, the state of our tributaries, but it doesn't tell us why these things are happening. And so this is kind of the launching pad to go out and design those studies to really understand why the Pike River has such a high nitrogen concentration, for example, that you can see as you're working through with CODAP. So that could be a really cool way to engage your students and think about how would you go about learning or trying to figure out why the Pike River has a high nitrogen concentration. So yeah, just to give you an idea, Winooski and Missisquoi rivers delivered from 750 to 2,000 metric tons of nitrogen to the lake. So just think about those rhinos floating downstream. Again, it's just a lot of nitrogen. It's a big system, and it's really fun to try to wrap your head around it.
Cool, thanks. All right, so basically, I wanted to leave you with not only the resources that we've been working on, but also some other resources. And so I will share a folder. In that folder, there is a document that actually just has a bunch of links. One of them is actually to the Gulf of Maine Research Institute dataset that I've been talking about. It includes a dataset actually and the challenge cards for the Gulf of Maine Research Institute. And then I've also included a link. CODAP has designed a bunch of sample datasets that you can play around with. They have them, you can see on the right of this slide, kind of some of the topics that they cover, and there actually are some others that are down below that you can't see that are simulations that you can run. And so really, I feel like we have just figured out a very basic level of how to use CODAP, but there are some other pretty advanced ways to run models and simulations and things like that. So you'll get that information in probably a follow-up email, but I can also post the link right now in the chat to that folder as well. And so I think, let's see if we want to go to the next slide. Great. And so we're actually done a few minutes early. I wasn't sure how many challenge cards to pose to you all. And so we'll actually go into the Q&A, which my colleague Nate is going to moderate. So I think since we're such a small group,